So we have seen the phenomenon of refraction, and twice I had made the mention of the word called refractive index. Refractive index appears for the first time in Snell's law, and that was the heading of the simulation also. So let us write that here. Snell's law. In Snell's law, I'll just write the mathematical format. I will not write the entire statement. N1 sin I is equal to N2 sin R. I prefer this approach to write Snell's law. Another very popular approach is sin I by sin R is equal to N. It is popular, but it is also equally dangerous. The reason is because you are assuming that one of the medium is air, and there is no logical basis on which you can just decide that one of the medium is going to be air. So this is the most comprehensive form of that law. N1 sin I is equal to N2 sin R. So from this we can write sin I by sin R will be equal to, sin R has come down here, so it will be N2 by N1. We know that I is the angle of incidence, R is the angle of refraction, and this is the mathematical sign function, and now our concentration is going to be more on the right hand side, that is N2 by N1. N2 is refractive index of the second medium into which the light ray is going to go, and N1 is the refractive index of the first medium in which the light wave was initially traveling. Now, majority of our discussion is going to be on how to define refractive index and why to define refractive index like that. Refractive index, by the way, in many books I have seen, it is given as refractive index is the ratio of sine of angle of incidence to sine of angle of refraction. It is wrong. Refractive index is not defined like that. Refractive index can be given as a ratio of sine of angle of incidence to sine of angle of refraction. But you can't say that refractive index is defined by that. The reason is, in the simulation just a few seconds ago we saw that when the light ray is falling normally on that interface, did it bend towards left hand side? No. Did it bend towards right hand side? No. So where is the deviation there? So I is 0, R is 0, and if you start defining refractive index using I and R, then you run into a trouble here, because you can't even define sin I and sin R, especially when sin R is in the denominator, and that ends up becoming 0. Therefore, there is a more fundamental definition for refractive index. Let us look at that now. Refractive index of a medium, and here I would like to add a word called absolute refractive index. Absolute means you can understand it in a way like the ultimate, right? So the absolute refractive index of a medium is defined as speed of light in vacuum to speed of light in that medium. Now, since we are considering medium 1 and medium 2, let us add subscripts to this. Refractive index of medium 1 is the ratio of speed of light in vacuum to speed of light in medium 1. Similarly, refractive index of medium 2 will be given as speed of light in vacuum to speed of light in the medium 2. Now, another important question is, why is refractive index defined in terms of speed of light? All that I can say at this stage is, when you are there in 10th class, understanding refractive index in terms of speed of light, you may find it a bit difficult. But once you come to 12th class, there is an entire chapter dedicated to it called electromagnetic waves, where there will be a detailed discussion how certain electric and magnetic properties correlate to give rise to refractive index. You will come to know about that at that stage. But as of now, you can just remember that refractive index is defined like this. Now, this is the definition. No exceptions to it. Whether you take I is equal to 0 or I is equal to 30 degrees, I is equal to 90 degrees, it works absolutely wonderfully in all the cases. So, this is absolute refractive index of first medium, absolute refractive index of the second medium. But here we are speaking of vacuum. We can't arrange vacuum, right? And in most of the cases, light will not travel from vacuum. It will travel from air to water, or water to glass, glass to kerosene, kerosene to Pepsi or thumbs up. Anything is possible, right? Why will light travel in vacuum for us? Even we can't live in vacuum. So we need a better understanding for that. Whenever light travels from one medium to another medium, then you can speak of refractive index of one medium with respect to the other medium. This is given by refractive index of the first medium by refractive index of the second medium. Now make use of these equations here. Therefore, refractive index of the first medium with respect to the second medium is given by refractive index of the first medium is C0 by C1, and now instead of writing in the denominator I am going to reverse it and write it here. Therefore, it will be C2 by C0. C0 and C0 gets cancelled. Refractive index of the first medium with respect to the second medium is therefore the ratio of speed of light in the second medium to speed of light in the first medium. Notice the reversal in the ratio here. Refractive index of first medium with respect to second is speed of light in the second medium with respect to that in the first medium. That is one thing that we observe. Second is absolute refractive index of any medium can never ever be less than 1. The reason is because if absolute refractive index has to be less than 1, then the denominator has to be more than the numerator. But denominator is speed of light in the medium, and speed of light in the medium can never be more than the speed of light in vacuum. Therefore, this value has to be greater than 1. Using the same logic, absolute refractive index of some other medium also has to be more than 1. Now coming to relative refractive index, if I write N12 here, then it is C2 by C1. Had I written N21, then it would have been C1 by C2. So if C1 by C2 is more than 1, C2 by C1 should be less than 1. So the moral of the story is relative refractive index can be more than 1, it can be less than 1, it can be equal to 1 also, not absolute refractive index. Absolute refractive index absolutely should always be more than 1. You can remember it that way. This is one thing. All this argument was in terms of speed of light. There is another argument to this. Refractive index of a medium is also given by wavelength of light in vacuum to wavelength of light in the given medium. This at this stage it might be a little difficult for you to understand, but I hope you have at least heard this word that light actually consists of electromagnetic waves, electric waves oscillating, magnetic waves oscillating and all that. How frequently the oscillations occur? I am intentionally using the word frequently because that is basically the frequency of the wave that we speak of. How frequently the particles oscillate is not decided by the medium. It is decided by the source which is oscillating it. Assume that you hold a rope in your hand and you keep oscillating it from one end. So how frequently the rope oscillates is decided by you. Similarly, when light is emitted, the frequency of oscillation is decided by the oscillator. Having said that, once the frequency is generated by the oscillator, that cannot be altered later on. So the frequency remains constant throughout the propagation. But when light is propagating from one medium to another medium, speed of light changes. Now correlate all this. Speed of light changes, frequency has to remain constant. It means wavelength has to change. The reason is because speed is given by product of frequency and wavelength. Frequency remains constant, speed changes, so it is obvious that wavelength also has to change. That is one thing. And look at it purely from a mathematics point of view. This is in the numerator, this is also in the numerator. So the way the speeds decide a quantity, wavelength will also decide the quantity in the same way. So you have wavelength of light in vacuum by wavelength of light in the given medium. So refractive index of the second medium will be wavelength of light in vacuum by wavelength of light in the given medium. Now correlate both of them. Refractive index of one medium with respect to the other medium will be, just like using the earlier logic, wavelength of light in the second medium by wavelength of light in the first medium. This is about refractive index. I hope all of you understood this. Now in the next session, what we will be doing is, I will be addressing the next important question that is faced by most of the students, which is kind of considered to be very dreaded by the students, and that is sign convention in case of mirrors, and that is to do with reflection of light. Thank you very much.